Welcome to this session on operations research. In this session, we will be discussing about simplex method of solving LPP. We have already seen whenever there are two decision variables involved in an LPP and also constraints, we can solve a two decision variable problem or a two decision variable LPP by graphical method. Sometimes when more than two decision variables are involved, then graphical method cannot be applied. So in such cases, whenever you have more than two decision variables involved, or even in cases of two decision variables, you can use simplex method for solving LPP, provided that the problem is represented in the format that is specified for simplex method. Also, all the constraints and the objective function will have to be represented in the form of new equations, where you will be introducing new set of variables called as slack variables which will be represented as s1, s2, s3, etc., depending upon wherever they need to be placed in the constraints or in the objective functions. So in a nutshell, simplex method is a procedure or a method used to solve LPP when graphical method is not applicable, and sometimes even in two decision variable problems graphical method may be applicable. You can also use simplex method. So basically simplex method is used to solve LPP when more than two decision variables are involved. Let us see what simplex method is, what is the procedure of solving simplex method, and how do you interpret the solution of simplex method. Let us take a problem now and see how simplex method is applied. Let us take the first problem in simplex method. Solve the LPP, solve the linear programming problem using simplex method. The problem is maximize z is equal to x1 plus x2 plus 3x3 subject to the constraints 3x1 plus 2x2 plus x3 less than or equal to 3 and 2x1 plus x2 plus 2x3 less than or equal to 2, x1, x2, x3 greater than or equal to 0. You can see here in the objective function there are three decision variables, so this cannot be solved by graphical method. And also you can see here there are two constraints and a non-negativity constraint here. So the first thing that you have to observe here is there are three decision variables in this objective function. Objective is to maximize z, x1 plus x2 plus 3x3, three decision variables involved, which are subject to two constraints 3x1 plus 2x2 plus x3 less than or equal to 3 and 2x1 plus x2 plus 2x3 less than or equal to 2. The non-negativity constraints, the values of x1, x2, x3 will be greater than or equal to 0. So in this case, what you have to do now is check what is the inequality sign here. The inequality sign is here less than or equal to LHS. The LHS is less than or equal to RHS here. The left hand side is less than or equal to the right hand side in both the constraints. So in a standard form, this is a standard form of say simplex method. So whenever you have such constraints here, which means LHS is less than or equal to RHS in both cases. So something has to be added here to LHS to bring it equal to the right hand side. So here you can see LHS is less than or equal to RHS, which means something has to be added now to LHS. So we now introduce two slack variables S1 and S2. Since there are two constraints here, there are two constraints. Of course, this is common to all problems. Most of the problems will have this non-negativity constraint, so this is not taken into account. I'm talking about the equations. The equations where the decision variables are present in the constraints. These are the constraints. So there are two constraints here. So you add two slack variables now, S1 and S2 respectively to the two constraints. And also you will add this particular S1, S2 or show this S1 and S2 in the objective function to make it into the standard simplex model. Okay. So the same thing, same model which was given, same LPP which is given to you now will be now shown in the form of a standard simplex. Let us see here. Maximization z is equal to x1 plus x2 plus 3x3. So here you can see here the same equation now is represented here. But you can see here these two slack variables which are added to these constraints are also shown. So what you'll be doing here is in this particular equation you will add add the first slack variable, that is S1 and convert it into an e and so if you add S1, if you add something here, if you add something, you can see here S1 is added, change the equality sign. So 3x1 plus 2x2, add S1 and make it into equality and make it into equality. Make it or bring it into, make it into equality. So it was inequality sign, now less than or equal to sign. Now what it becomes, by adding that slack variable S1 into this particular equation, now you are adding S1 and making it into equality. So you can see here the same first constraint here, this constraint, the first constraint here, this is the first constraint. It is now 3x1 plus 2x2 plus x3 plus 1 S1. You have added a slack variable with the coefficient of 1. Always in the constraints, the slack variables will have a coefficient of 1. Okay, coefficient of 1 which is equal to 3. Similarly, here also what you will do is you will add another slack variable, S2 which will also have a coefficient of 1. You can see here this is equation 2 or the constraint 2. You add the slack variables to the left hand side because left hand side is less than or equal to RHS. You add a slack variable and that slack variable will balance this LHS and RHS. So once you add the slack variable with a coefficient of 1, then that LHS will be equal to RHS. So you are now adding slack variables to first constraint as well as the second constraint. And also you express this in as non-negativity. So x1, x2, x3 and s1, s2 will be greater than or equal to 0. Will be greater than or equal to 0. So this is, you can see here in the constraints the coefficients will be 1. S1 you have added to the first constraint with a coefficient of 1. S2 you have added to the second constraint with a coefficient of 1. The same S1 and S2 you are showing in the objective function but with the coefficients of 0 because they don't exist in the objective function because they are not, no, they are, this S1 and S2 are slack variables. So they will have a coefficient of slack variables S1 and S2 will have a coefficient of 0 in the objective function and will have a value of 1 or the coefficient of 1 in the equations. You have to keep this point in mind. So your final representation of the objective function will be x1 plus x2 plus 3x3 plus 0s1 plus 0s2 subject to 3x1 plus 2x2 plus x3 plus 1s1 is equal to 3, 2x1 plus x2 plus 2x3 plus 1s2 is equal to 2, x1, x2, x3 and s1, s2 will be greater than or equal to 0. This objective function is now expressed In this way, maxima z is equal to x1 plus x2 plus 3x3 plus 0s1 plus 0s2 subject to 3x1 plus 2x2 plus x3 plus 1s1 is equal to 3, 2x1 plus x2 plus 2x3 plus 1s2 is equal to 2. x1, x2, x3 and s1, s2 will be greater than or equal to 0. Now we have to now construct a simplex table, an initial table, and represent all these values in this particular table. Now the standard format of the simplex table is expressed here. You can see here in the screen. You can see here the table here. This is called as the simplex table. You can see here, since there are say 1, 2, 3, 4, 5 variables here in the objective function. We have 5 variables in the objective function, and you have 2 constraints here. You have 2 constraints. Since you have 2 constraints, so here what will happen now, in the basis, this is the basis in the table, you will have 2 basic variables will represent. Initially s1 and s2 will start as the basis, as the variables here. This s1 slack s1 and s2, s1 and s2, that will come in the basis. Now let us see what each of these terms and numbers indicate. So let us see first what are these numbers. First, the first row here, please indicate, you can just look at this particular table here. See Cj is written. Cj here is the coefficient of the variables in the objective function. Coefficients of the variables in the objective function. You can see here all the variables here in this objective function are written here. You can see here x1, x2, x3, s1 and s2. And the coefficients of each of these in the objective function. The coefficient here in the objective function of x1 is 1. So 1 is written here. Coefficient of x2 is again 1. So 1 here. Coefficient of x3 is 3. Coefficient of s1 is 0. We have written 0 here. And coefficient of s2 is 0. So you have represented it in this particular way. This is the basis or the basic variables. We are starting off with s1 and s2 here. The coefficients of s1 and s2 are written here. These coefficients 0, 0 are written here. This is the s1, s2 table. The coefficients of s1 and s2. And then the solution. The solution here represents the constants, the right hand side numbers or the constants of the right hand side numbers of the constraints here. Whatever you can even call it as a constant now. These 3 and 2 are the right hand side numbers of the constraints. Okay. So here in this particular table here, just look at this particular table. Now how will we write? Let us just start by 1. So this is already shown here. This x1 is represented here. You can see here this x1 is represented here, and the coefficient of that 1 is the coefficient of this particular x1. So this thing is understood now. Now let us go to the second row in the basis. So you can write here in the basis whatever is the coefficient of in the first constraint. You can see here this is the first constraint. This is the first constraint here. So in the first constraint, the coefficient of x1, is 3. So you will write here 3, the coefficient of each of these variables in the first constraint. Coefficient of x2 is 2 in the first constraint. The coefficient of x3 is 1 in the first constraint. Of s1 coefficient is 1, and 0, s2 has a coefficient of 0 because s2 is not written there, but you can assume that s2, even if s2 is there, the coefficient of that will be 0 there. That is why we have not written s2, not indicated s2 in the first constraint. You can even write this equation as 3x1 plus 2x2 plus x3 plus 1s1 plus 0s2 in the first equation. You can represent s2 also, but with a coefficient of 0. Similarly, in the second equation or the second constraint, the coefficients will be 2, 1, 2, 0. S1 will have a coefficient of 0. S2 will have a coefficient of 1. And these right hand side values, in the first constraint it is 3, and in the second constraint this right hand side value is 2. Right hand side value is 2. So this is how you write the fill the table of the initial table in simplex method.
First, in the bases, you will write S1 and S2. They are the initial basic variables with the coefficient of 0. In the Cj row, you will write all the coefficients of the variables in the objective function, and in each of the rows corresponding to the basic variables, under each variable you will write the coefficients in the constraints. Okay, and under solution you will write the right hand side values of the equations, of the constraint equations. Now what are this Zj? What is this Zj value here? What is this Zj value? This Zj value is calculated this way. Your Zj value will be always your Zj value will be your Cb value, Cb, whatever x values you have, whatever x values, these x values you have here 3 is 3x1. You read this as a equation. If you read this as an equation now, just see the first equation, 3x1 plus 2x2 plus 1x3 plus 1s1 plus 0s2 is equal to 3. Similarly, 2x1 plus 1x2 plus 2x3 plus 0s1 plus 1s2 is equal to 2. That is the second constraint. Okay. Now what is this Zj value? Zj value is this 3, this value 3 into 0 plus 2 into 0. 3 into 0 plus 2 into 0. Similarly, that value will come here. So in this case, 3 into 0 plus 2 into 0 will be 0 itself. Similarly here, 2 into 0 plus 1 into 0, that will be again 0. 1 into 0 plus 2 into 0 is 0, so on. So you will write all these Zj values by doing this multiplication. So let us now see this particular table. This is the same table now which we saw in the previous slide. So here you have calculated the Cj minus Zj values. Now if you see here carefully, this is a maximization problem. And the condition is, for optimality, if all Cj minus Zj values, Cj minus Zj values is less than or equal to 0, then we say optimality is reached. For a maximization problem, if all Cj minus Zj values are less than or equal to 0, then we can say that optimality is reached. But in this case, you can see here all Cj minus Zj values here are greater than or equal to 0. Optimality is still not reached. For optimality to be, if we want to get the optimal solution, we can only conclude that this problem has reached an optimal solution is if Cj minus Zj values are less than or equal to 0, because this is a maximization problem. So if Cj minus Zj value is less than or equal to 0, then for a maximization problem you have reached an optimal solution. But here Cj minus Zj is greater than or equal to 0. You can see all these values here are greater than or equal to 0. 1 is greater than or equal to 0. 1 is again, 3 is again greater than or equal to 0. So now what you have to do, select the maximum amongst this. Maximum Cj minus Zj value corresponding to these values, whichever variable it is associated with. So in this case, the maximum value is this 3. And that corresponds to x3. So this now becomes your selected column, or which this is called as the key column. So this will be now called as the key column. So this now becomes your key column. This is your key column. Because this column has the highest or the maximum Cj minus Zj value. So that column is selected, and that column is called the key column. And the variable which is associated with that, x3, this x3 now becomes the entering variable. We call it as the entering variable, which we show as EV, entering variable. So this x3 will now come into this basis. That x3 will come somewhere here in this basis. This x3 will come somewhere here now. Let us see where it will come. Now that you identified the key column, choosing the highest Cj minus Zj value, you have now chosen this column. So the variable associated with it will now become the entering variable. Now let us take the ratios. The ratio for each row now, for this particular row where we have S1, this first row, the ratio will be this solution value, which is 3, divided by this key element here. This is not the key element, this is in fact the key column element. The key column element, the element corresponding to the key column in that particular row. So the element in the key column in that particular row is 1. So 3 by 1 will be 3. So this is the ratio for this particular row. Similarly, for this row, the solution is 2 divided by the key column element in the second row is 2. So 2 by 2, which is equal to 1, which is equal to 1, which is equal to 1. So you get a ratio of 3 for the first row corresponding to S1. Ratio of 2 by 2 is equal to 1 for the row corresponding to S2. Now choose the minimum of this. Choose the minimum ratio. Minimum positive ratio. Minimum positive ratio. Negative value is not considered here. Positive minimum. So the minimum, both are positive, and the minimum is 1 here. So it is the second row. The minimum ratio here corresponds to the second row. The second row now becomes your key row now. This now becomes your key row. The second row now becomes your key row. The second row now becomes your key row. This particular element is intersection point of the key row and the column. This intersection point of the key column and the key row is called as the key element or the pivot element. Key element or the pivot element. This is called as the key element or the pivot element. The intersection point of the key row and the key column now becomes the pivot element or the key element. This is now the key row. This now becomes your key row. Key row. And this 2 is the key element. So now what happens? X3 corresponds to the entering variable. Now that variable corresponding to the key row here is S2. So S2 now will be the leaving variable. S2 will be the leaving variable now. S2 will be the leaving variable. S2 will be the leaving variable. So this is the table, initial table now with the incoming and the outgoing variable. Incoming variable now will be x3. Incoming variable will be x3. Outgoing variable will be s2. So this column is the key column. This is the key row containing s2, and this you can see here a cell that is highlighted, that is the pivot element, the intersection point of the key row and the key column. So your new table now will have x3 as the basis. Now x3 will come in the basis now as a basic variable, and s2 will leave. X3 will have a coefficient of 3 in the new table now, and it will come here instead of S2. X3 will come with a coefficient of 3, and all the other values in the table will be calculated according to the calculations shown in the next slide. You can see here the column containing X3 is the key column and the row containing S2 is the key row. The outgoing variable is S2, incoming variable is X3. The intersection element of the key row and the key column is called the key element. In this case, the key element is 2. Convert this element into 1 by dividing each element in key row by 2 and the remaining elements in the key column as 0 using the formula new element in the new table, that is new element in the new table is equal to old element minus the product of the key row element and the key column element divided by the key element. New element is equal to the old element minus the product of the key row element and the key column element divided by the key element. What is key element? What is key row element? What is key column element? We have already seen, I have already told in the previous slide. Now row 1 calculations. If I say row 1 calculation, in the first row, the new element in the first row will be old element was 3 minus the product of 2 into the product of 2 and 1. The key row element was 2 and the key column element was 1, divided by the pivot element 2. So 3 minus 2 divided by 2 will be 3 minus 1 is equal to 2. So these values can now be entered into the new table. Whereas for row 2 was the key row. So the key row, all the elements in the key row will be, you can see here, all the elements, intersection element of key row and key column, in this case key element is 2. So all the elements in row 2 will be divided by key element 2. So row 2 calculation is simple because that was the key row. So all the elements in the key row will be the previous element or the old element divided by the pivot element or the key element. For a key row there is no problem, divide all elements with the pivot element, whereas for the other row you have to use this particular expression or formula, new element is equal to old element minus product of the key row element and the key column element divided by the key element. So this is how your table will look now with the new values. You can see here x3 has now entered, x3 has entered the solution. Now we can see the coefficient of x3 has entered, and with the coefficient of 3, s1 remains as it is. You can see all these values. Again, you have seen here, just look at this, x1, x2, x3, s1, s2, this will remain as it is. These are the new elements here. Zj values 2 into 0 plus 3 into 1. 2 into 0 is 0 plus 3 into 1 is 3. Similarly, 3 by 2 into 0 is 0 plus 3 into 1 by 2 is 3 by 2. 0 into 0 is 0 plus 3 into 1 is 3. 1 into 0 plus 3 into 0 is 0. Minus half into 0 is 0. Plus half into 3 is 3 by 2. And solution 2 into 0 plus 3 into 1, that is 3. Now Cj minus Zj values, Cj is 1 for this column, 1 minus 3 is minus 2, 1 minus 3 by 2 is minus half, 3 minus 3 is 0, 0 minus 0 is 0, 0 minus 3 by 2 is minus 3 by 2. You can see here all Cj minus Zj values are all less than or equal to 0. Since all Cj minus Zj values are less than or equal to 0, the solution is optimal. So we can say here optimality is reached. And then once you have established that, confirmed that Cj minus Zj values here are all less than or equal to 0, for maximization problem the solution is optimal, then you look into the basis and you can see here, out of the 3 decision variables x1, x2, x3, only one appears here, x3, in the final solution when optimality is reached, and that x3 has a value of this solution 1, this value 1. x3 has a value of 1. So the solution to this problem is x1 is equal to 0 because x1 does not come in the final iteration here. When optimality is reached, x1 and x2 are not present here. So x1 is equal to 0, x2 is equal to 0, and x3 is equal to 1. This is the solution. x3 is equal to this part you have to tell. This is the value of x3. x3's value, the decision variable x3 will have a value, a solution of 1 here. So if I substitute this in the objective function, substitute this in the objective function x1 plus x2 plus 3x3, x1 plus x2 plus 3x3, that was your original objective function, you get a z maximum value of 3. So this is the solution to this particular simplex problem. So here please don't get confused with this value. This is the coefficient of x3 in the objective function, not the solution. Common mistake which is done is this is taken at solution. This is not the solution. This 3 is the coefficient of this particular x3 variable in the objective function. The solution of x3, the value of x3 is this value which comes in the solution, that is the value of x3 for which you have reached optimality, and when you substitute that in the objective function, x1 is equal to 0, x2 is equal to 0 and x3 is equal to 1, you get a z maximum of rupees 3. So this is the simplex method. So the solution to this particular problem is x1 is 0, x2 is 0 and x3 is equal to 1 and z maximum is equal to rupees 3. In our next session, on the next video, we'll take one more problem in simplex method and again gain some more insights into the simplex method. Thank you.